process to do things like build 3D reconstructions of objects from multiple images, and reason about, for example, the distance of points from a pair of cameras and that kind of thing. So it's a big topic, and the first thing we'll do in this first hour is we'll cover the necessary mathematics to talk about projection using homogeneous coordinates. So just a note that the handout I've given you now is for a double lecture, so obviously we won't cover 2 hours, then we've got 1 hour left today, so do bring it next time. Okay, so the learning outcomes then for this first hour are, we're going to describe how matrices can be combined, again with homogeneous coordinates, to perform rigid body transformations in 2D and 3D. We've come across this process already in 2D, and we're going to talk about how it generalizes to 3D. And in particular, there are complexities around how rotation generalizes to 3D. And we'll talk about compound transformations again, but in 3D instead of 2D. We'll talk about perspective projection and orthographic projection and how they can be modeled in these matrix frameworks. And we're going to probably get as far as talking about how to write perspective projection as a matrix and how the camera projection matrix is formed. But we probably won't, we certainly won't have time to talk about the applications of this maths to 3D reconstruction and point triangulation, which we're going to cover in the next hour. Okay. Well, I guess we've seen this slide the third time now on this course. So, and this is the slide showing how we can apply transformations to a point, P, using a matrix framework. And we've talked previously about how we can perform transformations such as scaling or shearing or rotation using various forms of M. And those forms are given here on the bottom. Just to recap, we have the scaling by scale factor S and X and the X and Y directions respectively, shearing by some coefficient Q, and rotation via this matrix here, which rotates us about a specific point, the origin, anti-clockwise by some theta, okay, to give us our image point P prime. We talked before about how that framework allows us to do all of those linear transformations, but it does not let us do another common form of transformation, which is to translate or shift that point about in the space. And in order to accommodate that kind of transformation, as well as the linear transformations, to make that superset of transformations we call the affine transformations, we use a matrix of this form, where we have a 3x3 matrix. But in order to use that 3x3 matrix, we have to invent an extra coordinate that we call the homogeneous coordinate, which on the input side here is shown as just a 1. Okay? And in particular, for this transformation here, which is a translation, this will have the effect of translating point x to its image x prime, such that x prime is equal to x plus tx. Y prime is going to be equal to y plus ty, and then the homogeneous coordinate is going to be equal to 1 because that bottom row is just fixed at 0, 0, 1, so it can't be anything else. And we talked before about how we can apply affine transformations by modifying those first 6 numbers, those numbers on the first two rows of that matrix. And if we modify the top left 2x2 matrix and leave the rest like the identity matrix, so the t's here would be 0, then that's the class of linear transformations. But as you can see, we can do more because we can set that linear block to be the identity and perform translations as well. Now, because we're not changing the bottom row of this matrix from 0, 0, 1, and we haven't talked about the function yet of that bottom row of that matrix, the output homogeneous coordinate will always be 1. Which makes it easy to forget that actually what we should be doing when we calculate the output of this transformation is taking x prime and dividing it by that homogeneous coordinate. Now, because it's 1, it's not going to do anything. Okay, so the output x will just be x prime. But as we'll see in this lecture, when we do start modifying that bottom row to do other things than the affine transformations, it will be important to divide by the homogeneous coordinate for the x prime and for the y prime. Yeah? So we must always remember to divide by that homogeneous coordinate. So is everyone happy with that framework? We covered it before. Yeah? Right. Now, Again, this is another recap slide, so I won't go into it in full detail again, but the takeaway message of this slide was that if I have a point P, which we are expressing in all of these lectures as a column vector, okay, then if we apply this matrix to P to produce a transformed point P, and then perform this matrix transformation on that output P, and then take the output of that and perform this matrix transformation on that P, we end up with P prime. We can perform that same operation simply by multiplying all of those matrices together into a single 3x3 matrix that we call a compound matrix transformation. And that will have the same effect. And in this particular example, the compound matrix transformation is for rotation around an arbitrary point, which is C, composed of Cx and Cy as its coordinates. And the operation here is to shift the whole space the P's in down by negative Cx, Cy. And because then C is on the origin, we can apply our standard rotation matrix, albeit in homogeneous form, to rotate anticlockwise about that point. And then we shift our space back again so that C lands up exactly where it was, but our P will have moved. Yeah? And that's our compound matrix transformation M. So it's important to note that the order of operations that are applied on P, counterintuitively, is from right to left, because P is a column vector. This is the usual way we express these transformations in computer vision. Sort of annoyingly, if you're looking at computer graphics textbooks, they almost always express their points P in a row form, and you'll see these expressions with the input P here, all these matrices transposed but composed in an intuitive way, equals P prime. So don't get confused if you're looking at a graphics textbook and you're wondering why this matrix always has a negative, on the other sign. That's probably why, as you're using row coordinates. Yeah? Okay. Now, importantly, this framework generalizes to higher dimensions as well. So if I'm now working with points in three-dimensional space, I've got an input point x, y, z. Okay, I can apply this homogeneous idea, invent this extra coordinate, this homogeneous coordinate, to make an input vector that is 4 long, and start applying affine transformations to this three-dimensional point using a 4x4 matrix. Okay, so that matrix has very similar format for the translation and the scaling operations. Here we can see the matrix for a translation. So this will have the output, as you can probably see by just sort of multiplying it through in your head, that x prime is going to be equal to x plus tx, y prime y plus ty, z prime z plus tz, and so on. So, I mean, I guess that's an easy format to remember, and you can see that the scaling matrix is very similar as well. We've got a scale factor on x, y, and z, and that bottom row is always 0, 0, 0, 1. It's 4x4. However, when it comes to rotation, things aren't quite so simple. When we talked about rotation in 2 dimensions, we talked about rotation about a point, specifically the origin, and we had a matrix for that. But when we talk about rotation in 3 dimensions, we're talking about rotation around one of the principal axes of the space, and in 3 dimensions there are 3. So we actually have 3 matrices to perform rotation when we're working in 3D. And one is for rotation around the x-axis, another for around the y-axis, and another for around the z-axis. And each of those is of the following form. And it will take us anti-clockwise about that axis by some theta degrees or radians, depending on how you defined your sine or your cosine function. And we call these transformations the Euler angles. And sometimes people also associate them with the names like roll, pitch, and yaw. For example, if you're in a flight simulator or something, you commonly use that terminology. If you take a look at the format of these matrices, they're quite easy to remember because they all have this format: cosine, sine, sine, cosine. But if you're working in the x, y, or z dimension, think about that as 1, 2, or 3, you can see that the first column and row are like the identity matrix. For the y, it's the second column and row, the third column and row, and it sort of shifts that block of transformations accordingly. So there's a little pattern to it, and you'll notice that for the rotation y, the sine is on the opposite side the sign of the sign is on the opposite side. So, and perhaps the most interesting one to look at would be the Z, because if you think about it, this is, if I have some axes here, this is my X and my Y, and my rotation around that was cosine, negative sine, sine, cosine, for rotation about the origin. If I'm now working in 3 dimensions and I've got a third axis that's maybe coming out into the room or into the board, however you like it, then, and I'm rotating about that axis, then it's effectively the same thing. It's rotating around that axis in this way. So the transformation on the X and the Y coordinate is the same, and the Z coordinate doesn't change. So if I'm here and I'm rotating about Z, my position on that Z axis is not changing. As you can see, it's just passing through that transformation. Does that make sense? So, so the way that we can affect a general transformation in this space using rotations is by rotating a point some amount of roll, pitch, and yaw, some amount around the x-axis, around the y-axis, and around the z-axis. And to some degree, it's arbitrary as to what order we decide to perform those rotations in. But as we'll see in a moment, it does have an effect. Okay, is everyone happy with that? Yeah? Okay, so another way of thinking about this system is to think about it in a mechanical system that's called a gimbal. And it's suppose that you have some points that are scattered on the surface of a sheet of metal, okay, which are the points P that we're going to rotate. Now, those points P exist in a 3-dimensional world. They're just stuck onto this bit of metal, and that bit of metal is pivoted such that it can rotate within another metal frame, which is this red frame here. So that axis that those points are pivoting on, yeah, that can be thought of as being a rotation around, let's call it the x-axis in this system. So we could say, well, I've got some matrix Rx, which we defined on the previous slide, and that is having the effect of rotating those points P some amount theta about that axis, about that pivot. Does that make sense? Imagine holding that red frame there and spinning that sheet of metal with a point stuck on it on that axis. Yeah? That's what that transformation outlined in purple there is doing. Now, I said that we would compose these transformations in some order. The order I've chosen is this, and the next one we're going to do then is to rotate those points about the y-axis. So imagine creating another metal frame, this green frame, that has another set of pivots on them that are orthogonal to the pivots on the x-axis. Okay, so we're going to call that rotation around the y-axis, and now we can imagine moving those points by rotating them some amount on the x-axis and also some amount on the y-axis, and now those will be that sum amount. That will be the thetas that we put into those transformations. I flick back just to remind us that these are just transformations here, these matrix transformations acting on that point. Yeah, everyone happy so far? And then finally, we're going to add our third axis by imagining yet another metal frame. And somehow suspending this frame, this green frame, such that we can pivot it in this direction, that's orthogonal to the other two directions, and that will allow us to pivot by some RZ amount, some theta that we put into the RZ transformation. And the result of those 3 transformations is our image of our points P prime. Yeah, does that make sense? So the point of constructing this mechanical device is to demonstrate that when we're applying a matrix transformation on a point, as we talked about all the way back in week 2, we can think about that matrix transformation as redefining the space the point lives in, and it's warping the space and the points along with it. And that's what's happening here. So our y is warping the space that was already warped by our x, which the points were stuck to. Yeah? And so on. Right. So this construction is called a gimbal, and in fact they exist in the real world, and ships and things, okay? They help reveal one of the problems that exists in this Euler angle rotation system, as it's called. So if I were to take the middle Euler angle, which in this case I decided was going to be RY, and I rotate it 90 degrees, so I set my theta for RY to be pi over 2, or 90 degrees, what's going to happen is that red frame is going to spin so that its two pivots, the pivots attached between the metal plate and the red frame, line up with the pivots of the RZ frame. Yeah? I've spun that red frame so that its two pivots line up with the pivots of RZ by rotating 90 degrees around the green pivots, the RY. Does that make sense? You see what's going on here? Just spinning that so that those two lines there line up with the RZ. What's going to happen in this system? Well, we've lost a degree of freedom, because now, if I vary my theta on Rx, what's actually going to happen is going to cause rotation of the points. It's going to create the same effect as changing the theta on Rz. Yeah? Because the pivots for Rx have lined up to those of Rz. So we lose a degree of freedom in our system. And we say that the system is in what's called gimbal lock. Okay? So I'll show you an example of this, a demo. Again, it's in the lab code. Okay. So let's first of all take a look at the code. Right. So let's not worry too much about the intro bit of the code. It's just setting up some axes. What we've got here is a loop for t instead of theta to go from 0 to 2 pi. So 0 to 360 degrees. And I'm setting three variables here, theta x, theta y, and theta z. And these are going to be the thetas that I input to my three rotation matrices, Rx, Ry, and Rz, which you'll see are defined exactly the same way I had them on that slide a few slides ago. And then what we're then going to do is make a compound matrix transformation by multiplying these three matrices together into one, and apply that compound matrix transformation to three lines, which we'll then draw in a loop that goes, as you can see, from 0 to 2 pi. So if I run this, you can see we've got red, green, blue. Those are the three lines that were initially aligned to the three axes of the space x, y, and z respectively. And you can see that because I've attached the loop variable, let me move this. See, I've attached the loop variable t to this theta x and kept y and z just 0. All this transformation is doing is just rotating about the x-axis, and you can see that the points are indeed spinning around the x-axis. So now what I'm going to do is take that t off theta x and put it on theta y. We're going to run it just quickly just to show we're now rotating about the y-axis. So the green is looking constant. And then we're going to change that to 0 and then put the loop variable on the theta z, and that's going to rotate about the z-axis. Okay? Now, as I say, what we're now going to do is show that if I take this theta y and change it to be 90 degrees, or pi over 2 radians, because MATLAB works in radians, then if I run this, you can see that we're rotating now about the z-axis, as we would expect, by attaching our t to the z-axis. But then look what happens if I put the t here on the theta x. Exactly the same thing. Yeah? So the system is in gimbal lock, and we've lost a degree of freedom. So, next time you watch Apollo 13 and Tom Hanks is saying, "Oh, I'm out of control, I'm in gimbal lock," and this is what's going on. He's got his three thrusters, and one of them is maxed out, and he's lost a degree of freedom. And this is something that we need to take into account, not just in shuttle control, but also in things like animation. When we parameterize a model and it has joints that are parameterized by Euler angles, for example, and the animator might move the model into such a position that they then lose a degree of freedom on that joint. So there isn't really isn't really a solution to gimbal lock, in the sense that if you use Euler angles, you're bound to get yourself into it. You just have to choose the ordering of these transformations such that your model is unlikely to become posed in a situation where its middle Euler angle is likely to be 90 degrees. What you could do, you might say, well, I could solve this problem by just simply grabbing a hold of that construction and just spinning it on the x-axis. Well, yes, but then you've got a fourth matrix there. You've still lost a degree of freedom. Yeah. And there are other types of matrix transformations that do rotation as well, like quaternions, that don't have this problem but have other problems. But we won't talk about those on this course. Okay. So in summary, then. We've seen that, that our transformations, our affine transformations in homogeneous form, generalize to 3D, where the linear transformations are populated into that top 3x3 matrix there, and we saw scaling, we also saw rotation, but you've got 3 rotation matrices in 3D. And we also saw that you could do translation there by manipulating that final column. But in all of these cases, the bottom row of the matrix has always been 0, 0, 0, 1, which means the output homogeneous coordinate will always be 1. However, there's a broader class of transformation, which we saw indeed last time we talked about this, which is the projective transformations, where we do manipulate that bottom row of the matrix to enable all degrees of freedom on that matrix. And when we do manipulate that row, we must always remember to divide by that homogeneous coordinate. Okay, so in what sorts of situations might we want to do that? Well, when we want to model projective transformations, the kind of transformations that take points in a high dimension and map them onto a low dimension. And a good example of that is perspective projection, which we need to understand in order to understand this imaging process of how 3D objects become 2D images for us to work with in computer vision. Because as I say, if we understand that, then we can start reasoning about the geometry of the 3D world from 2D images. Okay, well, the best way to understand projection is to first of all start with this thing called a pinhole camera model. And this is, I guess, a model of perspective that was invented around about the time of the Renaissance, when people were starting to reason about the geometry of the world in their paintings. Now, we use the same mathematics today to reason about rendering in 3D graphics. This diagram is sort of a simplified diagram of how it works. So imagine that we've got a tree in so we're working in 3 dimensions now. We've got a tree that is out there in the world somewhere, and we are standing here in this room, and we are observing that tree through a window. Okay, and that window is a 2-dimensional plane, yeah, set in the 3-dimensional world, and we're going to call that the image plane, and we're observing the image of this tree on that window. Okay, in this diagram, then, the distance the tree is away from us is distance d down the z-axis of our space. So z is distance away from us. And the height of the tree is y in an orthogonal plane. And we're just forgetting about the x for now. It will be kind of coming out of the board towards you or into the board. But we're going to disregard that for simplicity of the diagram. So the tree is d units, say meters away, y meters tall. And the image of that tree, the top of that tree, is going to be y prime meters high. It's going to appear y prime meters high on the window, on the imaging plane. Why? Because light travels, certainly in this context, in straight lines. So ray of light is coming from the sun, bouncing off the tree, the top of the tree, and it's then passing through the window in a straight line, ultimately to us, the viewer, where we're standing at what's called the focal point in the scene, the camera focus. So we can see actually that this is nothing more than a system of similar triangles. We've got 2 right-angled triangles here. We've got the triangle that has side D, Z, and then this long hypotenuse here. And then we also have this smaller triangle here that's also a right-angled triangle that is... Oh, sorry, this is not... I've misdescribed this, I'm sorry. So the tree is at distance z away. The window is at distance d away from us. Okay, so
the ratio then of the height of the tree to its distance is equal to the ratio of the height of the tree on the window and the window's distance from us. So we end up with this just simple ratio of y prime over d is equal to y over z. And you could express it the other way around, but that's a convenient way to express it for now, because it allows us to just multiply both sides by d and say that the height of the tree on the window, as it appears on the window, on our two-dimensional image plane, is equal to d times y divided by z. These are just numbers. This doesn't mean differentiate or anything like this, just three numbers. Okay? And that is you know, the same expression would apply also for x. So I'll pause there in case there are any questions on that. Is that okay? Okay. So this relationship, as I say, was discovered a long time ago, around about the Renaissance period, and people started creating very simple cameras using what is this model of maths which is called the pinhole camera model, and these devices were made as illustrated here. You have basically a box that has a little pinprick at the front of it. Light bounces around in the world as it does. Some of it will enter the box through that pinhole, and it will fall upon, well, in this case there's a mirror which is bouncing it up to an image plane that the guy is observing, and in fact in this case drawing on. But you know, if you wanted to simplify it, you could just say that this is just falling on the back of the box, and the back of the box is the imaging plane. Okay, so actually what's going on in the camera obscura, which is the name for this device, is that you have this setup here where you have your 3D object out in the world, the light rays are coming in, they're all crossing over at the pinhole, and then they're falling on the image plane. In fact, you can see that the image will be upside down. Yeah? So in the camera obscura, the focus is here, the imaging plane is behind it, and that's why the image is inverted. Can you see that? Because the top of the tree will fall below the bottom of the tree. But the light follows in straight lines. So we don't use that construction in computer graphics or vision. We use this one here on the left, where we imagine the image plane to be in front of the focal point. But in reality, the way images are formed, and this goes for modern cameras as well, is you will have a focal point and an imaging sensor behind it. Okay? But the mathematics doesn't change. The ratio of the height of this object on the imaging plane divided by the distance of the imaging plane from the focus is the same ratio as the distance of the object to its height. Is that okay? Yeah? Right. So conveniently, this perspective projection model can also be modeled in our 4x4 framework that we can do all of our other transformations in, like rotation and scaling and translation. And this particular matrix here encodes this perspective projection. It has D down the diagonal except for the final row, and the final row you can see is 0, 0, 1, 0. So this is not our usual format for the final row, which means the homogeneous coordinate will not be 1 necessarily. So we can see why this gives us the same relationship by just multiplying it out. We can say, well, look, for the x coordinate, it's going to be d times x. So the output is dx. For the y, the output is going to be d times y, dy. For the z coordinate, it's going to be d times z, dz. And then for the homogeneous coordinate, by having the 1 there, we're copying that z out and putting it there in that final row. And we remember that in order to obtain the true location of that point as a result of this transformation, we must always divide by the homogeneous coordinate. So the output is going to be, for the x-coordinate, dx over z. Hopefully I've written this on the slide. The output for the y-coordinate is going to be dy over z, which is exactly this. and the output for the z coordinate is going to be dz over z, so is d. So everything is going to be projected to a distance d away from the focal point on the image plane. Yeah? Okay. So first of all, does that make sense? Can you see how the pinhole perspective, this mathematics, this simple ratio is encoded then under that transformation? So this is convenient then because we can apply this 4x4 matrix framework to perform this transformation. And we'll see why it's convenient in a minute. Right. Well, if there are no questions, then let me ask you this question. How do you think that our angle, or our viewing angle of the world will vary as the focal length varies? And here I'm introducing this terminology, the focal length, which is just the name we give to D, the distance between the imaging plane and the camera focus. Well, think about the tree out there, the window on the wall. We're observing the tree through that window. If I start walking towards the window, reducing my focal length, am I going to see more or less of the world? More of the world, yeah. So if I'm seeing more of the world, but my window remains the same size, then the apparent size of the objects that I see, I need to cram more of those objects into that window. So the apparent size will reduce. Yeah? Similarly, if I stand all the way back here and look through my window, I can probably see my tree, but not a lot else of the world. So that tree will occupy pretty much the whole of my image plane. So cameras that have a long focal length, and as I say, in a real camera, the pinhole is like in front of the imaging plane, so the rays of light come in, they're intersecting, and there's a big distance between the imaging plane, the sensor, and the focal point. For long focal lengths, because we see a lot of one object and very little else, it has the appearance of making that object bigger, and when we say we've zoomed in on the object. So a zoom lens has a long focal length, and these are typical values. This is the same scene shot with a lens with a shorter focal length. We see more of the world, because we're closer to the window, as it were. Yeah? Does that make sense? So the field of view we have of the world, of our scene, is inversely proportional to the focal length. Okay. So, all right, so here I'm just repeating that matrix expression from the slide prior to the previous. I just wanted to say that sometimes in textbooks you'll see this expressed in two alternate ways, and indeed even in these slides you'll see it expressed in the first way, where instead of having a 4x4 matrix encoding this perspective projection, we actually have 3 rows instead of 4. We've actually omitted the third row, the z coordinate row. So here we're projecting our points, so we get x becomes dx over z, y becomes dy over z. We forget about z because we don't care because everything's been projected to z equals d, and we obviously have the homogeneous coordinate in there. So this is a shorthand way of writing the perspective projection matrix that discards that effectively useless information, which is where z lands up, because we know it's going to be at d. Yeah, and we can also express, if we don't like the fact there are d's at multiple locations in this matrix, for example, if we were trying to solve for d, as we'll see later, then we can express it in this alternate way where there's just a single d there. And if you want to multiply that out yourself to prove to yourself that it's equivalent, then feel free. So using this compact form then for the perspective projection matrix, we have P being multiplied. So we have a point in 3D being pre-multiplied by P, which projects us to an image of that point in homogeneous form. Does that make sense? Right. Any questions on that? Okay. every year I think I should remove this part, but I just say it anyway. So I guess when I was at school learning technical drawing, we were taught about vanishing points. We were taught when we had to draw in 3D that if I want to draw a cube, then if I was doing it in isometric, it would look like that. And because the further this side is away, eventually that will converge to a point if I were to continue these lines out. And we call these vanishing points. And we can think about drawing a cube that has 2 vanishing points, or we might think about drawing a cube face on like this, going into the distance so it has 1 vanishing point, and so on. And these are just sort of ways to think about how we would draw 3-dimensional objects. Forget about vanishing points. They have no relevance to the mathematics of this. This is just something that I just remember being confused about many years ago when I learned this. How can things have 1 or 2 of it? No, forget it. So this is why I shouldn't cover it. But anyway, but what you can see, I guess what is useful to take away from this image is that what we can see is that parallel lines in the real world, in 3D, converge to a single point in 2D. And that is a result of this perspective projection. There are other kinds of projection as well. So there's another type of projection that's commonly used in like architects' plans for drawing a 2D image of a 3D object, like a house, called orthographic projection, which is a very fancy name for just drop the Z coordinate. Okay, so in an orthographic projection, X and Y are unchanged, and we just drop the Z. So you could you could do that perhaps with this matrix. We don't really tend to use orthographic projection in computer graphics, but this is just an example of a projection where the distance an object is from the camera doesn't affect its XY coordinates, whereas obviously with perspective projection it does, because points that are further away have a smaller distance between them. If that lighthouse there at the end was closer to us, it would be taller. And we saw that relationship in those equations for perspective projection. Right, where are we? Okay. So, why is any of this of interest? Well, in computer graphics, we use these matrix equations to manipulate and project our objects. So if I'm working in a computer graphics package, like a CAD package, computer-aided design package, building models in 3D, or even if I'm writing a game that's 3D game, I can, of course, move my objects around my world by translating them, rotating them, scaling them, using these affine transformation matrices, so 4x4 matrices with that bottom row 0, 0, 0, 1. That is indeed how people tend to manipulate objects in pretty much every graphics library like OpenGL or DirectX or anything like that. Equivalently, I can change my point of view on an object by rotating or translating the object. And if I have an object and I rotate it, that's sort of similar to me just walking around and looking at the object from a different side. So the position of a camera in a scene can also be expressed using, for example, a rotation matrix to point the camera and a translation matrix to shift the camera around in the space. For example, you could use the focal point of the camera as the anchor. We shift it around in the space and then we point it in a different direction. So, in fact, the process of imaging points in 3D, like P, to produce an image of those points in 2D that I can put on a computer screen, is the process of, first of all, applying some translation or rotation to that point to express where the camera is relative to that object, and then, having come up with that output of those two transformations, applying the perspective projection matrix to that point to project that point from 3D down to 2D so that I've got basically XY coordinates to draw it on the screen. So P prime is a 2D point produced from P, which is a 3D point, by some rotation and translation followed by perspective projection using that matrix P that we saw here. Yeah? Longhand or shorthand. But if we use shorthand, we don't have to mess about with dropping the Z in that equation. So actually, this process of modeling the projection, sort of the imaging of a three-dimensional point to produce a two-dimensional image, can be given by this compound matrix transformation pi, which is just the product of those three matrices. Does that make sense? Just another compound matrix transformation. And we have special names, like what we do all the time in computer vision, for these things. We talk about the position of the camera in the world and its orientation as the external parameters, or sometimes the extrinsic parameters of a camera. So the extrinsic parameters are the relative position of the camera and the object in the world. Yeah? They're basically where the camera is and where it's pointing. The intrinsics, or internal parameters of the camera, are the parameters that live inside P. And in fact, we saw in this simple case that there's just one parameter, it's D, which is the focal length. So the focal length is an internal parameter of the camera. It's got nothing to do with where the camera is in the world, but it has a lot to do with the process of how much of the world it captures and how that camera acts. So the extrinsics are the position of the camera, the intrinsics are the internal parameters like the focal length. So the extrinsics are R and T, more specifically the values of theta and the shifts in T, and the internal parameter is that focal length D. Does that make sense? In this simple scenario, we'll see in a moment that there are some other internal parameters. So, and I'll leave off here, this is my last slide. Okay, just unpacking that equation a little bit further, we've got our pi as our compound matrix transformation that is some translation, which we know is just the identity matrix in 3x3 up there, which I've just called I. And then this vector here, which for reasons we'll come back to is expressed here as negative C. This rotation, that's sort of R and RT. So the values in R and RC would be our extrinsics, and then this projection here. And the way that we've expanded that P there is you said it's an identity matrix in that shorthand form, and that K is actually a scaling matrix where the focal length is down the diagonal. So it's just a 3x3 matrix where the first two elements of the diagonal are D, which have the effect of, when multiplied together, making that projection matrix we've just been talking about. Yeah? Shall I flip back to again? On the right, on the first row there. And we call that matrix K, and that contains the intrinsic parameters. So our camera projection process is modeled by this compound matrix transformation containing the projection and associated intrinsic parameters and the extrinsics, which are its position and its orientation. And we'll be coming back to this extensively in the next few lectures. Okay, so I realise we have 5 minutes left, but I leave that for questions if anyone has any. Everyone okay with that so far? Maybe worth reviewing just that hour, making sure you fully understand it before we jump off into the next lecture on Thursday. Okay, great. Well, let's leave it there then. Thank you very much.